the Bohr model of an atom. To understand this, we need to know what is light absorption and light emission. So whenever we take any object, let's say if this is an object and light shines on this object, when you pass light on this object, some of this light is absorbed by the atoms of the particles, okay, and that is called as light absorption. And sometimes if you take an object, some light is emitted, comes out of this object, okay, and that light that comes out of the object is called as light emitted. So light absorption occurs when an atom absorbs light energy from the surroundings, and light emission occurs when the atom has excess energy and it gives off energy through emitted light. Okay, that is light absorption and light emission. Now why does that occur? To understand that, we need to know what is Bohr's model of an atom. For example, flame test. If I take a loop like this, okay, a metal piece, a metal loop, and I dip it in a solution of calcium and I put and burn it off under the flame, then the solution will burn more like a orange color, okay, whereas if you dip the same thing in copper solution and you put it into the flame, it kind of gives you like the greenish bluish color. Okay, so what are these? These are flame tests that basically tells you what type of metal do you have in your solution, because different metals burn in different colors. Okay, for example, you might have seen some different color lamps that are used, okay, like the different lamps that are used in front of neon lamps that are used in front of the restaurants, which like the sign says open or closed, right? They could be blue in color, they could be red in color, they could be bluish, pinkish in color. So there are different color lamps that are available, right? Bulbs. How are we getting all these colors? Those colors are coming because of the atom, type of atom that is present, type of gas that is present inside that basically bulb. Okay, so based on the gas, it would give you a different color of light emission. Continuous spectra. So when we take white light and it passes through a prism, it gets split into multiple colors, and when these colors, like in a rainbow, they're all blended in with each other, right? So for our example, what you see here in this image, all the colors are blended in. There's very difficult to see where the red color ends and where does the orange start, right? So this spectrum is known as a continuous spectrum, when all the visible colors are blended into each other. Okay, what is a line spectra? Instead of this, when the light passes actually through a gas lamp. Okay, what is a gas lamp? It's a lamp like this where some gas is basically inserted into the lamp and the light is emitted by this gas. Okay, so the gas is trapped inside this lamp right here in this tube, and when the electric current passes through, it basically excites the gas inside of this and the light is emitted from this gas. Whenever it's a gas lamp, the light that comes out of it passes through a prism, it is going to separate into colors like this. You can see that this spectra that is emitted is different from the continuous spectra. In continuous spectra, we saw all rainbow colors and they're blended together. Here we are seeing specific color light, specific colors, lines of specific colors. Okay, or you can either say specific colors or you can say specific wavelength of light, right? And these are shown as lines. That is why this spectra is called as a line spectra. And what is this spectra? This is the emission spectra of a certain gas. So for example, this gas that you see here is a hydrogen lamp. Okay, when light from a gas lamp passes through the prism, it produces colors of certain energies called spectral lines. For example, light from hydrogen lamp contains only 4 lines of colors: red, blue, deep blue and violet, these patterns are distinctive, are called as line spectra. They are very distinct from each other, and these spectra are very unique to different elements. Okay, so every element has its own unique line spectra. These are some of the examples of line spectra. For example, helium looks like this, lithium, krypton look like this. These line spectra are unique to every element. Every element has its own unique light spectra. Just how humans have unique fingerprints, these elements have unique line spectra that they usually emit. Now, how and why do they emit this light? That is explained by Bohr model. So far, we know that there are atoms. In an atom, we have a nucleus inside, and then around it, there are electrons that are surrounding the nucleus. Bohr specified that the electrons are not just anywhere in this space around the nucleus. Bohr model specifies that the electrons are in energy levels around the nucleus. So, for example, there's this orbit called as 1, orbit number 2, orbit number 3, orbit number 4. So, electrons are in these orbits around the nucleus. Electrons orbit the nucleus, that's what he said. Now we know that they do not actually orbit the nucleus, so this is not correct, but that is what Bohr model specified. Another thing that the Bohr model specified is that only certain orbit energies are allowed. So these energy levels, they are called energy levels. Why? Because they have different energies, they have different levels of energy. The energy level number 1 has the lowest amount of energy, then number 2 has more, number 3 has more, number 4 has the highest amount of energy. So the farther you get from the nucleus, more energy it has. Okay, one very easy way to remember this is, for example, if you are walking a dog on a leash, if your dog has a lot of energy, it is probably going to walk away from you. It would have more energy, more excited, right? But if the dog has less energy, it will walk closer to you. So same thing here, when the electrons have less energy, they are closer to the nucleus, and when the electrons have more energy, they walk away from the nucleus. Okay, electrons, he said, can jump between these energy levels. Another thing he mentioned is said that these energy levels are quantized. So if you ever see this word that energy levels are quantized, that means they have a specific quantity of energy. Every energy level has a specific quantity of energy. That is the term quantized. That is what it means. Okay, electrons can jump between these energy levels. Light is absorbed or released when the electrons jump. So what does that mean? When we shine light, let's say if I shine light, if I give lot of light to these atom, what will happen? The electron that is present here will gain all that extra energy, and now because the electron has more energy, it is going to jump out of its shell and it will go to a higher energy level. Not necessarily 4, it can jump to any higher energy level. That is called as the excited state of the atom. Okay, when it absorbs energy. So when atom absorbs energy, electron jumps from lower energy level to a higher energy level. But when the atom jumps back, let's say this atom was in the excited state, at some point it will want to come back to its original location, and it when jumps from higher energy level to lower energy level, the extra energy is usually emitted. And this, sometimes the energy that is emitted in form of colors that is visible, and that is called as the emission spectrum. Okay, so an emission spectrum results when energy is absorbed by an atom and then released as light. These characteristic emission spectra are unique for every element and can be used to identify the element. An emission spectrum that consists of individual lines is known as the line spectrum, what we saw before, and that is how we get these line spectrum. Now remember, when an atom's electrons are in the lowest possible levels, the atom is said to be in the ground state. So when the electron is supposed to be here and it is here, electron that is supposed to be in shell number 2 is already in shell number 2. Those are called as ground state, when the electrons are in their lower energy levels. If the electrons jump to higher energy level, then we say the atom is excited. So for example, here, if the electron is here in the energy level 1, when the atom absorbs energy, the electron will jump to an outer energy level. For example, it went from number 1 to number 5. That is called as absorption. But when this electron comes back to the original state, that's when it releases energy. And this energy sometimes is released in form of color light that is visible to us, and that is called as the emission spectrum or the line spectrum. Now sometimes this electron can jump from, for example, 5 to 4, then it goes from 4 to 3, then it goes from 3 to 2, then it goes from 2 to 1, right? In each time it is going to release a different colored light if it is emitting a colored light, right? So that is why you see different line spectra, you see different colors, like you see something in red, you see something yellow, maybe something in blue. Why? Because different wavelength of light is emitted, because the energy difference between these orbits is different. For example, you can see here, this is how much far it is from the nucleus. Then energy level 1 and energy level 2 are farther away from each other. Energy level 2 and 3 are little closer. Then 3 and 4 is even closer. 4 and 5 are closer to each other. So the energy gap between these is lesser and lesser as you go away from the nucleus. So that is why, because these gaps are different, you see different color light that is emitted each time. This is showing for a hydrogen atom, when the electron jumps from, let's say, 6 to 2, 4, 5 to 2, 4 to 2, or 3 to 2, it emits different color lights. Okay, sometimes it's red, blue, indigo, or purple. So it gives you 4 different color lights. This is for a hydrogen atom. How do we know this? How can you know it? For example, when it goes from 6 to 2, it's going from energy level 6 to 2, so it's very far away from each other, right? The energy difference is going to be highest here. From 6 to 2, the energy difference is highest. When the energy is high, wavelength is low. So low wavelength and high energy, if you remember from the electromagnetic spectrum, that lies in the purple or violet color. The smallest energy is the lowest energy, is when it goes from 3 to 2. So the energy difference is the least here, right? When it goes from 3 to 2, it is low energy, which means it is going to be very high in wavelength. And high wavelength was around the red region. Remember, it goes from 350 to around 750. So it's around 700. The color is red. So this is around the red region. And when it goes from the highest to the lowest, it goes to the violet region. We can also calculate this using an equation which is called the Rydberg's equation. Okay, Rydberg equation can help you calculate exactly what is the wavelength of the light that is emitted and what is the energy of the light that is emitted. Okay, so these are the two equations for it. When an electron jumps from shell number n1 to shell number n2, we can calculate what is the wavelength of light that would be emitted. Okay, wavelength in meters, n1 and n2 are the positive integers. Okay, another one also, we can use this equation to calculate energy, how much energy is emitted, using the bottom equation. So again, these are constant numbers in the middle, and n1 and n2 are the shells that it is going from to which shell. Okay, so n1 and n2 basically tells you which shell is it jumping from to what shell is it dumping to. Question would be something like this: calculate the emission wavelength of photon that is emitted when an electron in a hydrogen atom drops from energy level 4, n equal to 4, to energy level 3, where n is equal to 3. Okay, so question is asking what is the wavelength of the light. So we will use the equation, this equation, okay, to find the wavelength. We are solving for wavelength. what is N1 and N2? N1 is the initial and N2 is the final energy level. Always remember that. N2 is the smaller, always the smaller one, and sorry, N1 is always the smaller one, and N2 is always the higher energy level. Okay, ignore where is it jumping from to where is it going to. Just remember, N1 is always the smaller energy level, N2 is always the higher energy level. So N1 is going to be 3 square and N2 is going to be 4 square. Plug it into the equation and we solve for lambda. That comes out to 1.875 times 10 raised to the minus 6 meters. If the question is asking nanometers, you can convert this to nanometers. Otherwise, you can just leave it at meters. Similarly, we can ask you a question about energy. So in case of energy, you use the second formula that we saw in the bottom, and same approach. N1 is going to be the smaller energy level, N2 is going to be the higher energy level.